Alright, so section 4.4 is going to be about evaluating a linear model. So the do's, the don'ts, and I'm also going to give you a few more tools. So the first big don't is don't try to fit a linear model to a nonlinear association. So don't try to put a circular peg into a square hole, essentially. So if we look at this is a graph of the time and the temperature. And if we have a computer system try to fit a linear line to a nonlinear model, here's the issue we have, is that it gives us the line y equals 58.37 plus 0.005. And this is an issue because if we follow the line on the plot at 1500 hours, aka 3 o'clock, then what our predicted temperature is, remember we have to follow the line, is it says that the predicted temperature is 65 degrees. So predicted is 65 degrees. Now if we look at what the temperature actually is, we'll actually look at the dot above 1500, that's the actual temperature. And the actual temperature is actually 10 degrees higher. So it doesn't make any sense. Alright, the second don't is don't think that correlation necessarily implies causation. So, it's easier to say that causation shows a relationship, but we need to be kind of more like lawyers when it comes to our wording and what we see. So for example, instead of saying one thing causes the other, we say there is an implied relationship. So one kind of ridiculous thing that I'll tell you guys is in a certain state, and this is totally true, you can Google it, what they saw was that as margarine sales, that's the fake butter, went down in this state, guess what else went down? Divorce rates went down. So does that mean that margarine causes divorce? No, that's ridiculous. It's probably just a coincidence. We can say that they're correlated. If you look at the data, there's no denying that there's a correlation. Maybe there's a really long chain of confounding variables between the two, but you would never say that one causes the other. For us to be able to say that one thing causes the other, we actually have to show that it happens every single time. A nice example of this is if you look at cigarettes. So for example, we know that cigarettes are correlated to lung cancer. However, if you look at any pack of cigarettes, it doesn't say smoking causes cancer. It says that it increases the risk, or that there's a high correlation, etc., etc. That's because I think that we can all point out some 98-year-old person that smokes a pack a day and is still kicking. So that one person means that it doesn't cause it because it doesn't happen every single time. All right. The third thing is that we want to be aware of outliers. So what our computer tries to do, or what our math tries to do, is that it tries to fit a line to every single piece of data the best it can. So when we have outliers, which we can see here and here, what they're going to do is that our math and our computer systems are going to try to get that line to get as close to all the data, including those outliers, as it can, so it's going to pull it up on this side and down on this side. The other thing it's going to do is it's going to mess with how closely related we think that these two variables actually are. So what we do is that we take those outliers, we note them, then we remove them and refit our line, and as you can see, we have a much better fit on the second plot. Our linear equation will be more accurate to do predictions, and we get a better idea of the actual relationship between the percentage earned in a class and the hours studied. So, not to give too much away, but I would definitely pay attention to this on any of your exams. We also say that outliers are called influential points. Okay, so if you're to write up a summary statement regarding the data of hours studied to percentage earns on an exam, what would you say? Well, you would say once we remove the outliers, it seems that there is a very strong relationship between the amount studied and the percentage earned. All right. Aggregated data, we're not going to be talking about this too much in this course, but it's still a good thing that you should know the definition of. When we aggregate something, what that means is that we group things together and then take their average. So, for example, let's say that we're looking at the resting heart rate and age of people. So right here on the left-hand side, when we just look at each individual, we don't see any trend. Okay, there's nothing really going on. However, if we take all the people in their 20s and then find their resting heart rate average, people in their 30s, 40s, 50s, 60s, and 70s, what we can see is that there's definitely a trend in their averages. Okay? So that is what aggregated means. It means you're not looking at an individual, you're comparing groups to each other. So when you're writing a summary and you're using aggregated data, you do have to be careful about your language. When you write up the summary for the scatter plot on the right, you would say the group average by age versus the resting heart rate. That way we know that you're not talking about an individual, you're talking about an entire group. All right, the next big don't, which I would also pay attention to for any of your next exams or knowledge checks, is don't extrapolate outside of your data's range. So again, we're looking at temperature versus time, and let's say we want to use the linear equation. Okay, that's the one that's presented above. We rounded it for down here to estimate the temperature at 2300 hours. So first off, notice that this data only goes between 600 and 1600 hours. So if we wanted to look at 2300, so that'd be 18, 20, 22, 2300 would be about right here. We'd have to go far outside of our data. So if we estimated the temperature at 2300 hours, if we plug that into our model, so if we took 2300 and we plugged it in for X right here, what we would get is we would get the temperature would be about 90.5 degrees Fahrenheit. Now here's the deal if you don't know, 2300 hours is 11 o'clock at night. If the hottest part of the day is at 4 o'clock p.m., which it typically is, so 1600 is 4 p.m., and the hottest part of the day was 75 degrees, does it make sense that at 11 o'clock at night it would be hotter than it was at 4 o'clock? No, and here's why this doesn't work, is because if we look at this linear equation, we assume that it's going to continue to go upward. Now, if we assume it's going to continue going upward, that means that the temperature is going to continue to rise, and that's why we see that it's estimated to be 90.5 degrees Fahrenheit. What does the temperature actually do? Well, it actually changes trend. What temperature actually does is that it increases until about 4 o'clock, the hottest part of the day, and then it decreases. So this is the actual, but when you extrapolate, you're going off of a prediction that that linear trend is going to continue. So if you extrapolate outside of your data's range, what you're doing is that you're not recognizing what could be a changing trend. So the key here is don't extrapolate because could be changing trend. All right. So the last thing we're going to talk about is how do we measure the goodness of it? So it's not enough to just find a linear equation. We want to know how good does that linear equation do at predicting our data. So we want to be able to discuss how good this model is. And that is where the correlation coefficient comes in, or I'm sorry, the coefficient of determination. Now, I'm going to nerd out really hard for just a second. So to find the coefficient of determination, the thing that tells you how good your line of fit is so beautiful because all you have to do is take your correlation coefficient R and square it. Doesn't that blow your mind how beautiful math is? That it's like, hey, do you want a percentage of how much data is pretty close to your line? Well, just take that other number you have and square it, and that's going to give you your coefficient of determination. Just absolutely wonderful. So a couple facts about this correlation, or the coefficient of determination, is that it's going to be a number between 0 and 1, and it's going to denote the strength of the linear association between x and y. So it's actually going to tell you the percentage of data that's closest to the line. Okay, so for example, if r is 0.922 and we square that, then r squared would be 0.85, which that means that 85% of the total variation in y can be explained by the, now don't forget this is important, linear relationship between x and y. That means that the other 15% is unexplained. Now be careful, just because our r squared is low, does this mean that we can't say that x and y have a relationship? No, it means we can't say that they have a no, that means that they just don't have what kind of relationship? Linear. So let's look at finding r squared and writing a verbal interpretation. So if we look at A, so I said do it for A and B, but I'll do it for A and then I'll let you guys do it for B on your own. We're given the r value, which is 0.7168, and we want to find the r squared and write a verbal interpretation. So r squared would be 0.7168 squared, which is going to give us 0.5138. Now, when we write a verbal interpretation, here's what the verbal interpretation is going to be. It's going to say that 51.38% of weight, that's our y variable, can be explained by the linear relationship to height. So whenever you're writing this out, remember, we're trying to explain the y variable using the x variable. So you're always going to try to explain the y variable using whatever the x variable is. So if 51.38% of weight can be explained by the linear relationship to height, what that tells us is that there is still roughly about 48% of weight that cannot be explained by height. So that could be explained by somebody's body build, it could be explained by their muscle mass, it could be explained by a missing limb. There's a lot of different other things that could cause a difference between weight and height. So that is all we have for chapter 4. Don't forget, in the last video I showed you how to use StatCrunch, so if you need to brush up on that, go ahead and look at the 4.3 video.